My name is Alex, and today I'm gonna talk about rendering weight of objects and avatars through liquid mass transfer in VR. I present this paper on behalf of my co-authors Martin, Johannes, Manuel and Niels. Sensing weight is fundamental for human interaction. Inherently, when we lift or hold objects, we sense their weight to understand their physical properties. This affects how we interact with them. VR technology should therefore aim to provide realistic weight sensations. In VR games, the game experience could benefit from the additional realism. VR training and simulations should make weight perceptible as well, especially when it relies on the transfer of skills learned in VR. It is, for example, important to feel the weight of a chainsaw when learning to use it through VR training. Apart from simulating the weight of objects, it remains a challenge to simulate the body weight of avatars in VR. For an immersive experience, VR designers aim to create a strong sense of embodying an avatar, the virtual alter ego of the user. Matching visual characteristics of the avatar amplify the sense of embodiment, and so it seems plausible that congruent body weight could enhance embodiment as well, right? However, this is still unexplored, and haptic technology to provide the weight cues required is still missing. Instead, haptic weight interfaces for VR were focused on the weight of virtual objects, and over the years, researchers have developed haptic technologies aiming to simulate the complex sensory input through which we sense the gravity forces of objects. Limit systematically reviewed these research prototypes, and they concluded that the shortcomings of techniques and approaches indicate that there's still a gap towards a robust weight simulation, and that it is still a big challenge to sense the weight of a virtual object with the absence of real gravitational forces. Well, what if we would not try to simulate these gravitational forces, but instead physically change the mass outside of VR? A method to do so was introduced by Niels et al. With the weight and volume changing device. System transfers liquid mass in or out of a bladder to change its weight. And gravity cup and vibrovate are two approaches to transfer this concept to VR. However, they reveal challenges that still need to be overcome. The flow rate needs to be tackled, with gravity cup needing 16 seconds to fill the device with 330 grams. So for vibrovate demonstrated absolute weight changes of 50 grams, so there are also challenges regarding the amount of mass to be rendered. Also, gravity cup's liquid inertia was perceptible, and the use cases focused on the simulations of liquids. Moreover, both are designed for one-handed interaction only, which is a problem of most research prototypes for weight perception. Hence, rendering weight using liquid mass transfer is promising, but we still need to overcome these challenges, and we still need to find out whether we can apply this concept to body weight simulation. To overcome these challenges, we developed PumpVR. The device comprises two handheld controllers whose weight can be adjusted dynamically through liquid mass transfer. This is accomplished by pumping water into or out of the controller using a hose connection to an external water reservoir. It can change the weight of the controller simultaneously or independently of each other. The device employs a bi-directional pump to allow reversing the water flow. 4 solenoid valves direct the flow of water, which is transferred between 3 water bags. Sealed, foldable bags were chosen as they contract under negative pressure, avoiding the perception of liquid inertia. 2 of them are placed inside the controller's plastic housings. HTC Vive trackers are screwed on top of these housings to enable positional and rotational tracking in VR. A control unit communicates with the game engine via Bluetooth and controls the flow of water, depending on the in-app event. PumpVR fills up to 500 grams of water per hand. A technical evaluation yielded that the maximum weight is reached at an average speed of 150.8 grams per second. We also found that by varying pumping duration, PumpVR can produce 5 distinct levels of weight at an average error of less than 5%. We developed 2 test applications using Unity 3D. The purpose of the first application is to demonstrate and test the system's ability to render the weight of virtual objects with different mass. The game requires the users to pull out a variety of items from the bag and use them to combat approaching enemies and block arrows. They can grab the object by touching a box collider at the back, and they can put the object away by reaching into the backpack again. Based on the item's real-world characteristics, we assigned each item one of 5 weight levels. An additional weight level of 0 was set for phases when no object is held in the hands. The purpose of the second application is to explore the use of PumpVR to render body weight. Users first embody a slim female or male avatar. Then the avatar's body fat and the weight of both controllers are increased simultaneously. To familiarize themselves with their avatar, users adopt body postures which they see on a poster. They can observe themselves in a mirror. The scene features an activity wall to engage the users while embodying the avatar. We conducted a study within subject design in which we engaged 24 participants in both test applications. We used controller as independent variable to compare PumpVR with standard HTC Vive controllers with static weight. Let's have a look at the results regarding object weight simulation. We found significantly higher realism scores for PumpVR. This demonstrates the capability of PumpVR to enhance realism in games or to enable a more natural depiction of tasks in VR simulations. We also found that PumpVR positively affected the enjoyment ratings, indicating that users had more fun using PumpVR for object interaction than with standard controllers. This further demonstrates how rendering object weight through PumpVR can enhance the VR experience. Regarding the embodiment of avatars, we found significantly higher scores for virtual embodiment. This means that the virtual body was more strongly experienced as one's own when PumpVR was used. These findings indicate that the additional weight exerted by PumpVR was associated with increased body fat. PumpVR therefore contributes to research on avatar embodiment and demonstrates exerting weight forces as a promising approach to simulate body weight in VR. Using PumpVR significantly increased perceived exertion. This shows that the additional weight was noticeable. We found a negative effect of PumpVR on self-perceived fitness, which indicates that participants attributed this additional weight to their own fitness being reduced, rather than to the extra weight they had to lift. These effects also suggest further use cases for PumpVR. PumpVR's weight adjustment might, for example, be used to indicate fitness-related attributes of game characters, or to add challenges during extra games. Let's wrap up the findings and conclude this talk. We developed a novel bimanual weight interface for VR. It features a wider range of weight at a higher speed than previous approaches. We showed that using it to render object weight can enhance the VR experience. We also demonstrated that weight-changing controllers can also be a tool to amplify virtual embodiment. Our findings also suggest further use cases that employ the manipulation of exertion or fitness. With this, I conclude this talk and welcome your questions.